Hello everybody, and welcome to the third video in this series. And today I will be talking about calculus and looking at some of the basic topics in this branch of mathematics. Calculus is the branch of mathematics that deals with the rate of change of functions, that is, tangent lines, tangent planes, and tangent hyperplanes to functions, as well as length of curves, areas, volumes, and hypervolumes under curves. Calculus was invented specifically for physics by Isaac Newton back in 1665 or 1666, so it is an essential tool to understand physics properly. In this tutorial, I'm going to start by reviewing some trigonometry, since calculus has to do a lot with trigonometry, as you will see, and I will also take a brief look at limits, since both differential calculus and integral calculus are defined in terms of limits. Finally, I will be talking about differential and integral calculus. I will not go into proving all the statements, but rather on stating some important results, techniques and rules of both differential and integral calculus for an introductory physics course on engineering. Just as a warning, this video is intended to be a quick refresher, not a complete course. This is the reason why I skip a lot of the theory and proofs. Otherwise, the video would be way much longer and it would lose its purpose. Yes, I know this video is long, but the material covered is the typical level of math required to successfully complete a first semester physics for engineering course. Now, before we start, I would like to mention that since this video is somewhat long and it is a lot to digest, try to get through the video in more than one session. That way you can actually learn to apply what is said here. I also suggest taking a calculus book and doing some exercises for both differentiation and integration, since it is through practice that you will get better and understand more of the material that is presented. So well, let's get started. Physics has calculus at its foundation. It was invented by Isaac Newton back in the mid-late 1600s. Sometime around 1666, when the Black Pest hit England. Newton was trying to determine the instantaneous velocity of a particle or the rate of change of a curve. Since no tools for it were available, he developed techniques to make this calculation possible, and that is how calculus was born. Calculus is the branch of mathematics that studies the tangent lines and areas under curves. Even if it sounds simplistic, there is much more to it than you can imagine. To learn something about calculus, it is necessary to learn something about trigonometry, algebra, and numbers. The last two topics I have talked about in previous videos, so I am first going to talk somewhat about geometry, in particular a branch of geometry called trigonometry. Geometry has always been one of the most interesting topics for human beings. Since prehistoric times to modern humans, the use of geometry has been crucial for survival. It was extensively used to explore and understand the world and environment around us. Geometry was used to survey land, view structures, find relations between stars for sailing, to predict the position of the sun to know when to plant and harvest, and a lot more important things. Today we use it for much more things that are no less important than the reasons mentioned above. And now, the study of classical geometry is based on how to construct shapes with compasses and straight edges and their relation to rational and irrational numbers. It is important to stress that we are not going to use calculus techniques to study geometry. That is called differential geometry, and even if we wanted to, we do not have the tools to do so yet. Triangles are important. Triangles are made out of straight lines so that they are easy to draw and their properties can be easily deduced. Triangles are also the simplest closed shapes that can be created with straight lines. In our case, we are going to look at triangles in a plane. When looking at triangles in curved geometries, things can get very complicated and out of hand very easily. So we are going to focus on triangles in two-dimensional flat geometry. In 2 dimensions, there are 3 different types of triangles possible: the equilateral triangle, the isosceles triangles, and the scalene triangles. Of course, within these categories, there are subcategories of triangles, but these are the only possible major types of triangles. In particular, the isosceles triangles are triangles that have 2 sides of equal length and a side of unequal length. This other side can either be shorter or longer than the other 2 sides. Just to make sure we have defined the other triangles, the equilateral triangle is a triangle that has all sides of equal length, and the scalene triangle is a triangle where all the sides have different lengths. But why are the isosceles triangles more important than these other kinds of triangles? The reason isosceles triangles are so important is the simple fact that out of these isosceles triangles you can build an irregular polygon. As you can see, the more triangles that you use to build a polygon, keeping the length of the two sides constant and setting them to unity, the shorter the other side will be. In the figure, the first shape that can be made out of isosceles triangles is, well, the triangle. The next one is a square, 4 sides. The next one is a pentagon, 5 sides. And then the hexagon, heptagon, octagon, nonagon, decagon, and so on. In the diagram, the shape on the bottom is a polygon with 10,000 sides. At this point, the polygon resembles more a circle than a polygon, at least visually. So the circle is the limit in which you have an infinite number of triangles. This procedure was followed by the ancient Greeks. In particular, this procedure was followed by Aristotle. He found that the perimeter of these shapes divided by the diameter, or 2 units, and as the number of sides became very big, this ratio did not change very much and approached the number 3.141592, and so on. This number is what later became known as pi. Now there are several things to notice here. The first one is that Aristotle did this by using approximations made by hand. The second thing to notice is that he did this without any knowledge of the number 0. Today the number 0 seems common sense, but at that time there was no notion of the number 0. Impressive, I must say. The third important thing is the concept of limit. Aristotle never actually calculated pi completely, and it is highly doubtful that he ever calculated pi beyond 3 or 4 significant figures. But he did notice that as the number of sides of the polygon became larger, this ratio would give a more precise number, but it would be never-ending. This is the notion of a limit. That is an essential notion for calculus. Defining pi is important since it is crucial to define the first identity. An identity is a relation that holds no matter what. Say that you have an equilateral triangle on a flat surface. Assume that you draw circle arcs of radius r1, r2, and r3 on each corner, and you measure their lengths represented by L1, 2, and 3. Now, if you divide the length of each arc by the respective radius, and then add these quantities, it turns out that for any triangle, these add up to pi. The quantity L divided by r is called the angle of the vertex. Some important remarks to consider. Angles are usually measured in degrees, since it is visually more comfortable. The scale runs from 0 degrees, that represents the absence of an arc, to 360, that is a full circle or a complete arc. Usually angles are represented with Greek letters. In this case, the angle is represented by the symbol theta. Notice though that L divided by r is a more natural way to measure the angle. These more natural units are called radians. And according to Math World, the radian is defined as the unit of angular measurement defined such that an angle of 1 radian subtended from the center of a unit circle produces an arc with arc length 1. The range of the angle in radians is from 0 to 2 pi, where 0 represents the absence of an arc and 2 pi is a full circle or complete arc. As you would expect, it is convenient to have a way to change between degrees and radians. To convert x degrees to question mark radians, the first step is to know that 360 degrees are 2 pi radians. Below we write x degrees in equal to question mark radians. Notice that the degrees on both equations are on the left and the radians are on the right. Now cross multiply both terms. It is pretty straightforward to solve for the question mark, that is the angle we are seeking for, in radians. To transform the angle in radians to degrees, it is just a matter of solving for x and making the proper replacement. For example, to convert 90 degrees into radians, we start by writing the question mark and replacing 90 degrees in the x in the equation. 360 can be written as 4 times 90 so that we can cancel out the 90 degrees in both numerator and denominator, finally simplifying to pi half. Of course, you can do this with whatever angle in a consistent way. The next triangle we are going to explore is perhaps the most important triangle, since it is the triangle where we get all the trigonometric relations from. This is the right angle triangle. The right angle triangle has an angle of 90 degrees, and the other two angles can take any positive value as long as they add up to 90 degrees. Take the sides that make the 90-degree angle, also called a right angle, and name the side of the triangle that is closest to the angle named theta as A, and the side of the triangle that is furthest from theta as O. Name the third side of this triangle as H. The signs named A and O are related to the H side by the Pythagorean theorem, where we define H as the hypotenuse and is given by the square root of the sum of the squares of A and O. Remember that this relation only applies to right angled triangles. We also know that the sum of the two angles is exactly 180 degrees once you change pi into degrees, so that you can write the angle phi in terms of theta as phi equals 90 minus theta. This helps us reduce the number of variables we have. Also, notice that the hypotenuse is longer than A or O. That is going to be relevant in a while. Before moving on to really define the trigonometric functions, I want to define some terminology. So if we have a right angle triangle, A is called the adjacent side to the angle theta, or just the adjacent. O is called the opposite side to the angle theta, or just the opposite. H is called the hypotenuse and is always longer than or equal to either of the two sides. Finally, if O and A are lengths or positive values, the ratio between O and A can take any value between 0 and infinity with the 0 included. But in physics, we will be working with coordinate systems, so it is somewhat more natural to define these relations in terms of the unit radius circle in a coordinate system. So let's define a coordinate system on a two-dimensional plane with x coordinates in the horizontal direction and y in the vertical direction, such that both coordinates can take both positive and negative values. In this system, you get 4 areas called quadrants. It is important to remember that in this system, the hypotenuse is always 1 unit long. The first quadrant is defined as the place in the plane where both x and y take positive values. In this case, the adjacent and opposite sides to the angle phi are both positive. In the first quadrant, the angle phi ranges between 0 and 90 degrees, with the 0 included but not the 90. In the second quadrant, the x coordinates are negative and the y coordinates are positive. Notice that now we have two angles, the global angle phi, where phi is greater than or equal to 90 degrees, but less than 180 degrees. You can also define an angle theta between 0 and 90 degrees by subtracting phi from 180 degrees. In this quadrant, the adjacent side to the angle theta takes negative values and the opposite side takes positive values. In a similar way, in the third quadrant, both the x and y coordinates are negative. The global angle phi is greater than or equal to 180 degrees, but less than 270 degrees. The angle theta between 0 and 90 degrees can also be defined by subtracting 180 degrees from phi. In this quadrant, the adjacent and opposite sides to the angle theta take negative values. And finally, the fourth quadrant is where the x coordinates take positive values and the y coordinates take negative values. The global angle phi is greater than or equal to 270 degrees, but less than 360 degrees. The angle theta between 0 and 90 degrees can also be defined by subtracting phi from 360 degrees. In this quadrant, the adjacent side to the angle theta is positive and the opposite side is negative. It is useful to pinpoint some of the properties of the quadrants that will be important to define trigonometric functions. In the first quadrant, the angle phi ranges from 0 degrees to 90 degrees. The sign of the adjacent side is positive as well as the sign of the opposite. Thus, the sign of the ratio between the opposite and the adjacent side is positive. In the second quadrant, the angle phi ranges from 90 degrees to 180 degrees. The sign of the adjacent side is negative and the sign of the opposite side is positive. Thus, the sign of the ratio between the opposite and the adjacent side is negative. In the third quadrant, the angle phi ranges from 180 degrees to 270 degrees. The sign of the adjacent side is negative as well as the sign of the opposite side. Thus, the sign of the ratio between the opposite and the adjacent side is positive. In the fourth quadrant, the angle phi ranges from 270 degrees to 360 degrees. The sign of the adjacent side is positive and the sign of the opposite side is negative. Thus, the sign of the ratio between the opposite and the adjacent side is negative. We now define the trigonometric functions. The trigonometric functions are defined to be the relations between the length and sine of the sides with the angle phi, based on the unit radius of the circle defined on this coordinate system. Now, just remember that the length of the opposite and adjacent side can only take values between 0 and 1. Even more, since the length of the hypotenuse is 1, then any quantity defined by the hypotenuse is itself, at least in this coordinate system. So we can infer that the opposite can take any value between -1 and 1, as well as the adjacent side. Since the hypotenuse has to be 1, once the value of, say for example, the opposite side, then the length of the adjacent side is also fixed, or vice versa. Be careful though, since you have to be careful with the sign that depends on the quadrant the sides are in. The procedure to get the relations are pretty straightforward. You can choose some angles between 0 and 360 degrees and measure the length of the opposite and adjacent sides. With this data, and considering the sign of the sides based on the quadrant they are in, make a plot of these values. Of course, these are just a few values, but you can kind of trace a smooth curve through these values to get the general trend of how these functions change continuously. In the case where the hypotenuse has a length of 1, the opposite side is defined as the sign of the angle phi, and the adjacent side is called the cosine or complementary sign of the angle phi. Before we move on, let's define what a function is, since this will be recurring terminology that we will use most, if not all, the time. A function is of n greater than or equal to 1 variable, is a mathematical entity that receives n mathematical objects as input and outputs another mathematical object by operating on these variables. The variables that the function takes can really be any mathematical object at all. Vectors, matrices, tensors, even text, real numbers, unicorns, whatever you can think of. And as it can take any of these objects, it can output any of these objects. In our case, we will be considering functions that take one real number and output another real number by means of the elementary operations of addition, subtraction, multiplication, and division. If f is a function and x a real number, we'll define the operation of f on x by using a hollow dot. This will be the equivalent of setting a comma-separated list of the variables in parentheses, that in this case it's just a single variable, and just besides this list, the letter f. Notice that this parenthesis denotes something like slots where only one variable of the type of the object can be placed. Notice that for functions of several variables, switching the variables does not always give the same result. To continue with trigonometry, you define the adjacent and the opposite sides as functions of the angle theta, when the hypotenuse has length 1. These two first trigonometric functions are called sine and cosine. We also get our first trigonometric identity, that sine squared plus cosine squared is equal to 1. And this should be no surprise, since this is how we define the opposite and adjacent side. Also notice that if the hypotenuse is not 1, we can get the opposite by multiplying the hypotenuse by the sine of the respective angle. Same for the adjacent, but using the cosine. that is consistent since the hypotenuse is the longest side and sine and cosine functions can only take values between 1 and -1. Just as a clarification, the adjacent or the opposite can only be as long as the hypotenuse when the angle phi is an integer multiple of 90 degrees. Of course, the integers including 0. We have already defined the sine and cosine, but it is worth to take a look at the relations once again. In these graphs, the quadrants are denoted by red lines. Of course, there is no reason to be limited by the logical range of the angle, but you can choose whichever angle in the range and extend these functions to this angle, following the trend and the logical steps. It is worth to notice that the positive angles are measured clockwise and the negative angles anti-clockwise. This definition has to do with the properties of the three-dimensional arrangement of the axis, but this we will ignore for the moment and just take it as a definition. I will now give some of the identities of the sine and cosine functions. The functions obey symmetry with respect to the origin. An odd function is a function that yields the negative value of the function when operating on the negative value of the variable. For example, if an odd function operates on x and it yields a value y, then if the same function operates on the value minus x, it will be the equivalent of operating on x and taking the negative value of the result, that is minus y. This is the case of the sine function. An even function is a function that yields the same value of the function when operating on the negative value of the variable. For example, if an even function operates on x and it yields a value y, then if it operates on the value minus x, it will be equivalent of operating on x and taking the value y. This is the case of the cosine function. Now, there are also translational symmetries. If you take the value of the sine function and evaluate it at the value theta, it is the same as evaluating the function at 180 degrees minus the angle theta. In the case of the cosine, it will yield the negative cosine. You can actually shift the sine and cosine to change one function to the other. The sine of an angle theta is the same as evaluating the cosine of the angle at theta minus 90 degrees and taking the negative value of the result. On the other hand, the cosine of the angle theta is the same as evaluating the sine of the angle at theta minus 90 degrees. Now, there are other identities that are related to the sum of two angles, and these identities are important since they are widely used in integral calculus. I will not prove them here, but they can also be easily proved using other mathematical techniques. And to finish this extensive discussion of trigonometric functions, we now define the tangent of the angle as the ratio between the opposite and the adjacent, or the sine divided by the cosine of the angle phi. Important to notice, tangent is not defined over all the possible angles, but it is defined in intervals of 180 degrees, starting at minus 90 degrees, where 90 degrees in radians is pi. Now, of course, the tangent function can be extended to any angle, but it is important to notice that this function is not defined everywhere, and you have to be careful when evaluating it. We also define the reciprocals of these trigonometric functions, and these have identities of their own, but they can be deduced from the sine and cosine identities. So now that we have discussed trigonometry extensively, we can now move on to some other notions that we need to have before starting to look at differential calculus. We now explore the concept of infinite and infinitesimal quantities. We will assume that we are working in the real numbers. Define infinity as the biggest positive real number possible. Also define an infinitesimal number as the positive real number that is closest to zero without it being zero. Of course, these quantities are impossible to write or even imagine, but the concept has to be there in some corner of your mind for calculus to work. Now, infinite and infinitesimal quantities are used to define limits. A limit is defined as the value that a function approaches as the input approaches a certain value. The concept of limit is essential in understanding calculus. So let's explore the concept of limit with the function f of x equals 1 over x. First of all, let's make a plot of the function. Let's first explore how the function behaves as x approaches, for example, 2. Let's write a few numbers of how the function behaves when it approaches 2 from numbers that are less and greater than 2. So as x approaches 2 from the left, that is some number less than 2, we can try a few numbers. We start somewhat far from the number we want to approach, that is 1.75. The result is approximately 0.5714, and so on. But 1.75 is somewhat far from 2. We certainly can do better. So as we take numbers that are closer and closer to 2 from the left, the function 1 over x converges to 0.5. You can do the same as x approaches 2 from the right, and you find that as you take numbers that are closer and closer to 2, the function 1 over x once again converges to 0.5. So we can conclude that since the function converges to 0.5 as x approaches 2 from both sides, the limit as x approaches 2 is 0.5. However, if you take the limit as x tends to 0, you find that from the left, the function approaches a very, very big negative number, or negative infinity. And as x approaches 0 from the right, the function approaches a very, very big positive number, or positive infinity. In this case, the limit does not exist. So in the video where we define real numbers, we defined that any finite number divided by 0 gave infinity. This was not very accurate, but we were forced to do that since we wanted to get a complete set of operations for the real numbers so we could use them for a practical purpose. We now make our definition stronger and take infinity as a limit, rather than a fixed number, that makes more sense than defining it through a specific operation. Of course, there are more rules and caveats when taking limits, but this notion should be enough to at least define the derivatives. It is now convenient to talk somewhat about straight lines and the rate of change that has to do with the steepness of the line. Now consider the two equations f1 of x equals x and f2 of x equals 3x. And we ask the question, which line is steeper? And we can find out by plotting the functions. And of course, we find that the second function is the steepest. But how can we numerically check this? So let's define the steepness of a line as the amount that a line represented by f of x changes in a fixed interval delta x. So if f1 of x changes more than f2 of x over the same interval, then f1 of x is steeper than f2 of x. So we define the steepness of a line as delta f over delta x, so that in this case, the steepness of f1 of x is 1 and the steepness of f2 of x is 3. I will now show you how to calculate this steepness in somewhat more detail. Let's take a look at how to calculate the steepness of a line. For this, we will use f2 of x equals 3 times x. The procedure step by step is to take two different values of x, say x1 equals 0.5 and x2 equals 1.0. Evaluate the function at x1 where f2 of x1 is 1.5 and at x2, f2 of x2 is 3. Now use the definition of steepness, delta f of x divided by delta x, that is f2 of x2 minus f2 of x1 divided by x2 minus x1. So when you plug in the numbers, the result is 3, as we expected. Just notice that you can also calculate it as f of x1 minus f of x2 divided by x1 minus x2. So just be careful that the order of the subtraction in the numerator is consistent with the subtraction in the denominator. Otherwise, you will get the positive and negative signs flipped. Now, consider the two lines described by the equations f1 of x equals 3x and f2 of x equals minus 3x. If you follow the outline procedure, the steepness of the first line is 3 and the steepness of the second line is minus 3. But how can a steepness be negative? This is just an unfortunate choice of words. The correct terminology to use in these cases is that we are calculating the gradient, not the steepness. The gradient indicates the direction in which the function is growing. A negative gradient indicates that the function is increasing towards the negative x direction. That is completely consistent with what we see in the plot. The bigger the magnitude of this gradient, the faster the value of f is increasing in the direction of the gradient. But hold on. Notice that this difference forms a right angle triangle, so actually delta f over delta x is the tangent of the angle shown. Now, two things to consider. The first one is that the angle is defined with respect to the positive x-axis. The second one is that the angle is defined between minus 90 and 90 degrees, where the negative angles are defined in the fourth quadrant. So how about if we have a general function? So assume that you have that the function f of x is continuous in an interval a less than or equal to x that is less than or equal to b. And we define the second as the line joining 2 points in this continuous interval, where delta f over delta x is the tangent of the angle that is shown. So let's start with the points relatively far from each other. As you can see, this line clearly crosses 2 points. However, as these 2 points are close enough so that they look as a single point or are separated by an infinitesimal quantity, then delta f is also an infinitesimal quantity, and the ratio is, well, possibly finite. Notice that now the second just touches a single point on the curve and becomes a tangent to the curve, or a straight line that barely touches the point on the curve. This way we have defined the derivative of a general curve, that is the value of the tangent of the angle of the line that barely touches the curve at a specific point on the curve. With this, we can define the derivative of a function of x with respect to x as the limit as delta x approaches 0 of the ratio of the change in the function over delta x. Of course, this is only one of the many ways to define the derivative, but all the methods to define the derivative are equivalent, so this is more than good for us. So it is time to start giving examples of derivatives, and I will work through some examples of derivatives of at least some of the common functions. Let's start with the derivative of a constant function, or a function that does not depend on x. So let's start with the definition of the derivative as the limit as delta x tends to 0 of the change in the function divided by delta x. This clearly implies that the derivative of this function is given by the limit as delta x approaches 0 of 0 divided by delta x. Now, this is important since we now come across the notion of limit and infinitesimal quantities. Notice that when we take the limit when delta x approaches 0 of 1 divided delta x, the result is plus or minus infinity, depending on the side from which the quantity approaches 0. So we have the case of an infinite quantity multiplied by 0 that is clearly not well defined. And this is where the concept of infinitesimal comes in. Remember that we have defined that in the limit as delta x approaches 0, delta x is a number that is as close to 0 as any other number, but it is not exactly 0. But c minus c is exactly 0. So the derivative with respect to x of a function that does not depend on x is 0. And this is our first major result. We now start looking at more sophisticated derivatives. Assume that you want the derivative with respect to x of a linear function of x. Let the function be given by some non-zero constant c times x plus a constant b. Again, we started with the definition of the derivative, and using the definition of the function, we can now expand the polynomial and cancel the corresponding terms, leaving us with a simple limit that yields c as a result. So the derivative of a first-order polynomial is the leading coefficient c in the expression. Now, two things to notice. One, we have dropped the subscripts 1 and 2, and 2, it is convenient to use x plus delta x instead of a different variable, since it helps to locate the variable delta x, that is the variable defining the limit. And we now want to take the derivative of a real polynomial. Define a function of x that is given by a real non-zero constant c times x raised to a positive and integer power n. So we can use the definition of derivative, and following the usual procedure, we get the following terms. At this point, we have no way of knowing what this limit gives, since we encounter a term that is given by x plus delta x, and this sum raised to this positive and integer power n. And we can't really cancel the delta x in the denominator, at least in a straightforward way. So before we proceed, let's remember how to expand the sum of two terms, or the expansion of a binomial raised to an integer power n. So starting with n equals 0, any number raised to any power 0 is 1. If this binomial is raised to the power of 1, then the expansion is the sum of the two terms. How about if you want to expand this binomial to the second power? If you follow the procedure, this expansion with the binomial gives a squared plus 2 times a times b plus b squared. You can proceed again the same way with the expansion of the binomial to the power of 3 and get the result. So, is there a pattern when expanding a binomial to the power of a positive integer n? The answer is yes, and the key lies in the definition of Pascal's triangle. The ith row of Pascal's triangle gives the coefficients for the expansion of a binomial raised to the power I. Now remember that to construct Pascal's triangle for a certain row, you must use the coefficients of the previous one. So for example, the first number of the third row is 1, that is the first number of the second row. The second number of the third row is the first number plus the second number of the second row. The third number of the third row is the sum of the second and third number of the second row. And the fourth number of the third row is the last number of the second row. And I have provided the fourth row so you can check that you understand the procedure. Now, to get the coefficients of the nth row, you use the coefficients of the binomial distribution. The first coefficient is given by the binomial and 0, the second one by binomial and 1, and so on, where binomial nk is given by n factorial divided by n minus k factorial times k factorial, where the positive integer n factorial is defined as 1 times 2 times 3 times all the integers up to n, and 0 factorial is defined as 1. So we can now expand the binomial to any integer and positive power n. So the expansion yields x to the n. The second term, x to the n minus 1 times delta x to the first power. The third term, x to the n minus 2 times delta x to the second power, and so on, with every term multiplied by the respective binomial expansion coefficient. But the important thing to notice is that after the second term, delta x is raised to a power greater than or equal to 2. So when subtracting x to the n from this expansion, the only terms that are left are the ones that involve delta x. So when dividing the remaining terms by delta x, the only term that will not have delta x is the first term that has binomial coefficient n. When we take the limit delta x tends to 0, then the only term that survives is again the first term. Finally, concluding that the derivative of c times x to an integer positive power n is c times n times x to the n minus 1. But what about if n is not necessarily a positive number, but a real number? The procedure to get the derivative of x to the power of n, where n is a real number, is much more complicated than when dealing with n being an integer number. But you can follow the rule of thumb that the derivative with respect to x of x to the n is given by n times x to the n minus 1, except when n equals 0, that is 0. Just remember that x to the 0 is a constant function and the derivative of a constant function is 0. It is important to notice, though, that there is no polynomial that has 1 over x as its derivative. Other important derivatives are the ones of trigonometric functions. So let's first look at the derivative of sin of x with respect to x. Again, we start by using the definition of the derivative, that is the limit when delta x tends to 0 of sin of x plus delta x minus sin of x, and all of this divided by delta x. Now this is when the double angle identities become useful, and we can find sine as the sum of two terms as shown. Now the limit when delta x tends to 0 of cosine of delta x yields 1, so that the signs in the numerator cancel out and we are left with cosine of delta x times the limit when delta x tends to 0 of sine of delta x divided by delta x, where this limit yields 1. But why? And the reason is quite simple, but let's take a look at this in a more graphical way. Notice that if we define a circle of radius 1, the length of the arc L will be the angle x times the radius r. So the length of the arc will be x units, if you measure the angle in radians, of course. Thus, as we have already seen, the opposite side to the angle is given by the sine of x. The important thing to notice is that as the angle gets smaller, the length of the opposite side that is given by the sine of x starts to approach the length of the arc that is given by x. Of course, it is not exactly the same, and actually, when x is sufficiently small but still finite, the sine of x is given by x plus corrections of order beyond x to the power of 3. So, when x is infinitesimal, or in the limit when x approaches 0, sine of x divided by x is 1. And just in case you are wondering, along the same line of reasoning, as x approaches 0, the cosine of x can be written as 1 plus corrections of order x squared and beyond. So we can easily see that the derivative of sine of x with respect to x is cosine of x. Following the same procedure, we can take the derivative of cosine of x, and the derivative of cosine of x with respect to x turns out to be minus sine of x. So always be careful with the sign. Now that we have looked at the derivatives of some functions, we can try to get some other derivatives. I will only present the results for the elementary functions, but if you need more derivatives, you can always look at a table of derivatives that can be found in books and the internet in general. So the derivative of sine of x with respect to x is cosine of x. The derivative of cosine of x with respect to x is minus sine of x. The derivative of tangent of x with respect to x is secant squared of x. The derivative of x to the power of n with respect to x is n times x to the n minus 1. The derivative of the Euler number to the power of x with respect to x is itself. The Euler number is commonly known as e. And the derivative of the natural logarithm of x with respect to x is 1 over x. So just remember that the natural logarithm is the logarithm in base e. So the natural logarithm of e is 1. Again, remember that from the properties of logarithms, you can write any number to the power of x in terms of e to the x, and the logarithm of x in any base as a natural logarithm. So I know that I didn't mention the derivatives of some elementary functions, but any other elementary function that you can think of is contemplated in more complete derivative tables. So far, we have just contemplated elementary functions. But what about if two elementary functions are the sum of elementary functions, or a multiplication of elementary functions, or it is a composite function of elementary functions? Fortunately, there are some rules for these cases, and I'm going to mention them briefly. But first, to simplify the notation somewhat, I'm going to use a capital D with a subscript x to refer to the derivative with respect to x. The first rule is the linearity of the derivative, meaning that the derivative with respect to x of the sum of two or more functions is the sum of the derivative with respect to x of the functions. And the derivative with respect to x of a function times a constant is the constant times the derivative with respect to x of the function. For example, the derivative with respect to x of the sum of 2 times x to the 3/2 plus sine of x is 2 times the derivative with respect to x of x to the 3/2 plus the derivative with respect to x of sine of x. That, after some simplifications, yields 3 times x to the 1/2 plus the cosine of x. Then there is the product rule. That means that the derivative with respect to x of the product of two functions is the derivative with respect to x of the first function times the second function plus the first function times the derivative with respect to x of the second function. For example, the derivative with respect to x of x times sine of x is the derivative with respect to x of x times sine of x plus x times the derivative with respect to x of sine of x, that after simplification yields sine of x plus x times cosine of x. Finally, there is the chain rule that says that the derivative with respect to x of a composite function of x is the product of the derivative of the outermost function with respect to the innermost function times the derivative with respect to x of the innermost function. So, for example, if f of x is the function e to the x and g of x is x squared, then using g of x as the innermost function means that f of g of x is e to the x squared. So the derivative with respect to x of this composite function, f of g of x, is the derivative of f with respect to g, that is e to the g, times the derivative of g of x with respect to x, that is 2x. So the result is 2 times x times e to the x squared. Of course, people usually include the quotient rule, but it is a combination of the product and the chain rule. Try it yourself and see if you can get it. So, just to finish the review of differential calculus, let's give a brief summary of the things we have learned. The derivative of the function is the gradient of the tangent line at a point on a curve. Of course, the definition of the derivative is the first concept we have to consider. We define the derivative with respect to x of a function of x as the limit as delta x tends to 0 of f of x plus delta x minus f of x, and all of these terms divided by delta x. I will not mention the derivatives of specific functions, since those you can look up on the table of derivatives, but I'm going to mention the useful rules to differentiate functions. The first property is the linearity of the derivatives. If you have a sum of functions of x, the derivative with respect to x of this sum is the sum of the derivatives with respect to x of the individual functions. Also consider that the derivative with respect to x of a constant times a function of x is the constant times the derivative with respect to x of the function. There is the product rule that says that the derivative with respect to x of the product of two functions of x is the derivative with respect to x of the first function times the second function plus the first function of x times the derivative with respect to x of the second function. Then there is the chain rule that says that the derivative with respect to x of a composite function f of g of x is the product of the derivative with respect to g of f times the derivative with respect to x of g. One thing that I didn't mention is that we have been getting the general trend of the derivative of the functions. To get the derivative of the function at a specific point, you have to take the limit as x approaches this specific point. If the limit as x tends to the specific point does not exist, then the derivative is not defined at that point. So with this, we finished now with differential calculus. Of course, we have just scratched the surface of differential calculus. We have just defined the first derivative. But of course, you can take 2, 3, 4, whatever number of times the derivative of a function, and this will have different meanings. But this should be useful enough to complete a first semester course on physics. Now we are going to continue into integral calculus. So we now want to calculate areas under the curves. Areas under rectangles and triangles are easy to calculate. If you have a constant function, say f of x equals 2.5, and you want to get the area between the x-axis and the value of the function, the value in this case is very simple to get, since the area of a square is the width times the height. That in this case is 2.5 times 4, that equals 10. If you have a line that has a positive slope and passes through the origin, say f of x equals x, and you want to get the area between the x-axis and the value of the function, The value in this case is again very simple to get, since the area of a triangle is the width times the height divided by 2. That in this case is 4 times 4 divided by 2, that equals 8. Say that we want the area under the graph for a general curve. Of course, the first approach we can take is to approximate the area under the curve with rectangles. You can approximate the area with big rectangles that go over the curve, but this will give us a bad overestimate of the area. Or we can use the big rectangles that go under the curve, but this will give us a bad underestimate. Or you can approximate the area with small rectangles that go over the curve, but this will give us a bad overestimate of the area, but way better than the big rectangles, for sure. Or you can approximate the graph with small rectangles that go under the curve, but this will give us a bad underestimate of the area, but still way better than with big rectangles. Now you could think about getting an average value for the area using the over and under estimate, and for sure the estimate could improve, but it is still far from giving an exact value. So what can we do to make this estimate into something exact? Because for applications we need, something exact. So if the area is represented by a sum of rectangles, we can calculate the area of the ith rectangle by taking the value of the function at x plus I times delta x times the width of the rectangle delta x, where delta x is constant throughout the interval and is given in terms of the size of the interval that is divided into n rectangles. Of course, the total area is the sum of all of these rectangles, and you can over or underestimate the area. So in the limit when n tends to infinity, we define the integral. The sign for the integral looks like an elongated S that stands for continuous sum. But how do we represent the integral? Is there any relation of the integral with the derivative that we can use to simplify our calculation? And the answer is yes. And it turns out that integration is the reverse process of differentiation. The proof is not easy and it is somewhat long, so we will just assume that it is true. Now, integration is much more complicated than differentiation. Oftentimes, all you can do is use techniques to search for an integral and not really use formulas for integration. Integration, as opposed to differentiation, is an intuitive process. Of course, there are techniques that we can use, but just be aware that integration requires a lot of practice and some luck. So let's look at some integrals and integration techniques. The idea behind integration is to obtain a function that, when differentiated, gives you the function you started with. On the same hand, when you integrate the derivative of a function, you will get the function, plus an integration constant that we will discuss in a while. Let's now take a look at the integrals of some of the basic elementary functions. As for the differentiation case, let's take a look at the integral of a constant. If b is a constant real number that doesn't depend on x, the integral of b with respect to x is b times x plus a constant c. The integral of x to the n with respect to x is x to the n plus 1 divided by n plus 1, if n is not equal to minus 1, plus the integration constant. The integral with respect to x of 1 over x is the natural logarithm of x plus the integration constant. The integral of e to the x with respect to x is e to the x plus the integration constant. The integral of natural logarithm of x with respect to x is somewhat more difficult to evaluate and is given by x minus x times the natural logarithm of x plus the integration constant. The integrals of trigonometric functions are also important, and the most simple and straightforward ones are the ones for the sine and cosine functions. The integral of sine of x with respect to x is given by negative cosine of x plus the integration constant. The integral of cosine of x with respect to x is given by sine of x plus the integration constant. All of the above are the same integrals of the most common encountered elementary functions. Now let's take a quick look at some of the basic techniques that you can use to calculate integrals. The first technique is that of simple substitution that is based on the chain rule of differentiation. Remember that the derivative of the composite function f of g of x is given by the derivative of x with respect to g times the derivative of g with respect to x. If you can identify a function that has the form of the derivative of a composite function, you can substitute this to eliminate terms and make the integral simpler. For example, the integral of x times the sine of x squared, you can see that if u equals x squared, then the derivative with respect to x of u is 2x. Using the geometric meaning of dx, we can solve for x times dx so that x times dx is the u halves. And we can replace this in the integral equation to get a simpler expression to integrate. Of course, we can now easily integrate the sine of u with respect to u. That is minus 1/2 times the cosine of u plus the integration constant c. The final step to get the integral with respect to x is to replace u by x squared as we had defined it. The following technique is that of integration by parts that is based on the product rule. Remember that the derivative with respect to x of the product of two functions of x is the derivative with respect to x of the first function times the second function plus the first function times the derivative with respect to x of the second function. You can solve for one of the terms, say that you want to solve for the term of the derivative with respect to x of the first function times the second function. You can now integrate both sides of the last equation, and using the properties of integrals, you get the following result. This result tells you that if you can identify the integral as the integral with respect to x as the product of the derivative with respect to f of a function f times another function g, it might be easier to switch this integral to the integral with respect to x of the function f times the derivative of g plus f times g, since this term comes from an exact derivative. Let's look at an example of this. Say that you want to integrate x times sine of x with respect to x. In this case, we cannot really use the chain rule since the derivative of x is 1, so simple substitution is not possible. To use integration by parts, choose the derivative with respect to x of f of x as sine of x and g of x as x, such that f of x is negative cosine of x and the derivative with respect to x of g of x is 1. Now, when you make the substitutions into the equation, you can see that you are left with a very simple integral, that is the integral of cosine of x with respect to x, that is of course sine of x. Getting the final result that the integral of x times sine of x with respect to x is minus x times cosine of x plus sine of x plus the integration constant. If you have any doubt that this is the integral, you can always take the derivative to check the result. Another technique that is very common is that of trigonometric substitution. Say, for example, that you want to find the integral with respect to x of the square root of 1 minus x squared. At simple glance, there is no obvious way to solve this integral equation. And you can try integration by parts, but you will get redundant equations, and the square root of 1 minus x squared is certainly not the result of the chain rule. So how about if we use trigonometric functions to see if we can get a simpler expression to integrate? Assume that x equals sine of u such that dx is cosine of u times du. Replacing these values in the function, we get an integral with respect to u that at first sight looks more complicated than the original integral with respect to x. But remember that cosine squared of u plus sine squared of u is always 1. So we can solve for cosine squared of u, that is 1 minus sine squared of u. That way, we can simplify the integral to that of cosine squared of u with respect to u. But it still looks complicated for this. And for this, you can use the double angle formula to simplify to an easier integral that finally yields that f of x is 1/2 of the sum of u plus 1/2 of the sine of 2 times u plus the integration constant c. The intermediate steps, I leave them to you. Now, it is obvious that u is a function of x and we want to get an expression that involves only x instead of u. And I will not go into that since that is a completely different problem. But just so that you are aware, it can be done and it is not as difficult as you might think. It just involves a lot of steps. So far, we have just defined the indefinite integral. That is, we have just gotten how the trend of how the area from the x-axis to the curve changes as x increases. We also have an undetermined constant c. But why? So remember that for real numbers we have an additive identity that can be added to either side of the number, and for real numbers this identity is 0. So when integrating we must consider this 0, and since the derivative of a constant function is 0, then the integral of 0 is a constant. So when performing the integral we must consider this 0 term just to be consistent, and this is called the indefinite integral of a function. Now, to get the area between the curve and the x-axis for a certain range, we need to define the definite integral of a function. And just as a reminder, and as we have seen, the indefinite integrals are important since this integral gives us the exact function of how the area between the x-axis and the function behaves as x increases. But what about if we want to calculate the area between a and b, where a is less than x, that is less than b? The strategy is to calculate the area up to b and then subtract the area up to a. So if capital F of x is the integral of f of x, then the area between the x-axis and the curve subtended by f of x is given by the limit as x approaches b from the left of capital F of x, minus the limit as x approaches a from the right of capital F of x. So remember that f of x must be continuous in this range for the definition to make sense. Just consider that the area over the x-axis is positive and the area under the x-axis is negative. Take for example the integral of sine of x with respect to x from 0 to pi, where the sine function is clearly positive. Notice that the area under the curve is 2 units and it is greater than 0. Now take the same integral but from 0 to 2 pi, where there is as much area above as below the x-axis in this range. Of course, in the first part the area enclosed is over the x-axis and it is positive, as we have already seen. And in the second half the area is under the x-axis and is the same as that of the previous half, but now it is negative. So the sum of both curves is 0. Notice that we didn't bother to include the constant c in either integrals, since when subtracting the functions, the constant immediately disappears. Finally, I want to give some properties and make a quick summary of integrals of functions. The first thing we saw is that the process of integrating is the inverse of differentiating. There are no specific formulas, but there are techniques to integrate functions. Both definite and indefinite integrals obey linearity. That is, the integral of the sum of functions is the sum of the integrals of the functions. Also, the integral of a constant times a function is the constant times the integral of the function. For definite integrals, there are several other rules. For this, we need f of x to be continuous in the interval less than a, less than x, that is less than b. If this is true, and c is some number between a and b, then the integral of f of x between a and b is the same as the integral of f of x between a and c plus the integral of f of x between c and b. If we try to set both the upper and lower limits the same, then the integral is 0. If you switch the integration limits, then the integral flips sign, and this is obvious just from the definition of delta x, if you consider the integral as a sum of rectangles. That, by the way, is called a Riemann sum, named after the German mathematician Bernhard Riemann. Also, and I have already mentioned this, but scalability for definite integrals is also valid. The definition of the integral of f of x times a constant is the same as the constant times the integral of f of x. Finally, the definite integral is the area under the curve. If you integrate a function from a to b and capital F of x is the integral, the area under the curve is the limit as x tends to b from the left of capital F of x minus the limit as x tends to a from the right of capital F of x. Important to remember is that when the area considered is over the x-axis, it is positive, and if the area considered is under the x-axis, then the area is negative. Of course, This is just calculus, integral calculus, for curves in 2 dimensions. I have not talked about integral calculus for multiple dimensions and will not even go into vector calculus. But this should be enough to at least use it as a tool for an introductory physics for engineering course. So just as a summary of the tutorial, we have looked at basic trigonometry and where the basic trigonometric functions come from. We also briefly discussed the concept of limit and how to calculate very basic limits. We have also looked at differential calculus, its definition as the tangent line to a curve, and how to calculate derivatives. We have also looked at integral calculus, specifically how to calculate integrals and how to interpret it as the area under the curve. Of course, I have just scratched the surface of both differential and integral calculus, and I have omitted many things, but for practical purposes, this should be enough to successfully complete an introductory physics for engineering course. Well, I hope that you enjoyed and learned from this tutorial, and I hope to be uploading the remaining math tutorials in the next weeks. If you liked the video, please give it a like and subscribe to the notifications for when the new videos come. See you in the next video. Bye bye.